So, couple things. I don't know if I have stuff to pass back or I got it back to you guys, but I will get it back to you. Logistics. We are on week 5. There are 15 weeks in a semester, plus a finals week. So that means after this week, we're a third of the way through our semester. This probably doesn't seem like we're doing the leaps and bounds jumps that you would have done in the fall, because, well, you know, as you get further in, it's harder and harder to make those big jumps. But we're moving pretty well through the material. So that means by the end of the week, you should have assignment and homework 5 in. And again, if you're working into them until next week, it's no big deal. But at some point, we're going to kind of catch up on that. If you look ahead, I believe week 7 is our first exam. So that will be 2 weeks from either today or Thursday. I'll let you guys pick which day you like the best. You let me know next time around. But look at your schedules. But 2 weeks from today, we'll have an exam. That week, I'll also give you your first project here. All right. So, which is in addition to the other work. So just looking ahead, thinking logistically what's going on. Any questions on that? You guys doing good on stuff? All these classes are built the same, intentionally to make sure that, you know, hey, I understand. I have an assignment here, and a lab here, and a lab here, and now I'm gonna have a couple projects go on. Did you look ahead to see what we're covering this week?
Kirchoff's laws.
Yes. Wow. Oh, you printed assignments out ahead of time.
Yeah.
You can also read the text ahead of time. All right, so we've already talked about these a bit. So what I want to do, I'm going to go ahead and reiterate them. Actually, I'm going to go write them over on the other board so I can leave them sitting up there the whole time while we work on stuff. So I'll put them as far over here as I can. That way they're not in the middle of my normal workspace. Kirchoff's laws. There are 2 of them. I only talked about them last week. I know we've talked about it before. But so after Ohm's law, these are the most critical ones for circuits. Most basic. Kirchoff's laws. First one. At least the first one I used to talk about is the loop law, or the voltage law, or however you want to talk about it. The sum of all the voltage drops as I work around the loop is 0. Do I need to write that out in English, or saying it good enough? Going all the way around the loop, I have to sum to 0. So basically, it's saying, hey, if I start at point A, by the time I work around to point A again, everything I gained and dropped and gained and dropped ought to end up being 0. The other one is the junction law, or the current law. And that says the sum of all the current into a junction is equal to the sum of all the current out of the junction. Hopefully, when you start thinking of that, that seems kind of common sense. Hey, everything that goes in has to go out. I can't get stuff out that I didn't put into it. But I want to look at these. The loop law says, if I start here, and I'm going to draw kind of a box. So if I start at this spot, right here, go up, the voltage, now I'm going to draw them all as gains. So as I go around, I'm going up, 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 up. The sum of all those voltages is just equal to delta V1 plus 2 plus 3 plus 4. I just add them all together. And that'd be 0. Now for it to be 0, that means some of them are actually going to be losses in the polarity switches because we have the negative sign in front. or we have a negative sign in front because the polarity switches, whichever way you prefer to think. Generally go across sources of batteries, we're gaining voltage. Go across resistors, we're losing voltage. Of course, we draw a big circuit as possible that we have things that are working against each other, like two batteries pushing opposite directions or something. The junction law, I kind of ran out of room, but I'll stick it down the bottom. It says that I'm at a junction. I'll write this as I1, I2, and I'll draw this as I3, I4. It doesn't really matter how I write these. The sum of all those in equals all those out. Or in this case, I1 plus I2 equals I1 plus, equals I3 plus I4. Sometimes you'll see them drawn as all the currents in are equal to 0, which means some of them are just reversed. So all those either reverse direction or polarity, by just putting a negative sign in front of it means it's going the opposite direction. Or if I solve and I don't know a current direction in a junction and I add up all the currents and I get a negative number, it just means whatever I initially assigned is the wrong direction. All right, with this, we just want to look at some circuits. And I'm going to start with one. We did some I think we did something like this last week. Example. How about example? Yeah, there we go. Example. I have 5 volts. 3 volts. 8 volts. Find that delta V. And I do one real quick. Why did I put delta V's on here? What's delta? Like in algebra, delta just means change. Okay. When I go from one place to another place, it's the difference between them. Yeah. So a lot of times in a circuit, if you see just V1 or V2 or VA, it means the voltage at that point relative to wherever you pick the ground, which may not be across the one element. So a lot of times when you write delta V on these and these more formal statements, what we're really just saying is the voltage across that element. So it's not meant to be more confusing. It's just there to go, oh, we're just looking at some difference. And I know there's probably voltage on one side and another voltage on the other side, and what's the difference between them? Okay, so how do I find delta V? Well, this would be a loop. I'm going to start from right here. I'm going to sum all those voltages and work around. I'm going to go up 5 volts. So I'll actually write a plus. I lose voltage here, so I'm going down 3 volts. Going this direction, be careful. It's really tempting to look at these and you're on the other side. And I mean, it's reverse to this and think, oh, it's negative. But it's not, because it's the direction I'm moving in a loop. So I'm gaining voltage as I go this direction, going from a lower to a higher voltage. And I'm also, the direction the polarity gave me here, I'm gaining voltage as I go here. And this has to equal 0. Okay, at this point, I can, 5 minus 3 is 2, ends up being 10 volts plus delta V equals 0, so delta V equals minus 10 volts. So what that means is if I measured it, this polarity, it would be minus 10 volts. Or in other words, the actual voltage is drop that direction. That's why I get the negative sign. Yeah. Clear? Yep. Okay. I had some problems in the last homework that did this. It drew actual physical batteries. I'm going to be honest. I think, well, we'll try it. Let's see if I can draw. Created one this weekend. I don't remember who it was, but had issues with it. Maybe everybody had issues. But. So let's talk through this. So it must not, it's obviously not this week's homework. So I'm going to come in. I have a lead on each of these. I'll put the positive here. Is that so? Positive's on the left. I know it's probably small from your vantage point, but oops. And example, these are 6 volts each. And in that problem, these were labeled A, B, C, D, E, F, G, H. And there was a wire connected from here to here, a wire from here to here. And you're asked to measure different voltage. Do you remember doing that problem? So you bring my voltmeter along. And so I want to maybe find, so if I were to come in and I would put my voltmeter, and I put the red lead, assuming it's connected correctly in my voltmeter, okay? If I reverse the two, I'll reverse my polarities. On A, and the black on H, what reading would I get from the voltmeter? Yeah, it would be 24, and the positive is here, and the negative, we go ground, is here. So I would actually get 24 volts. And I wouldn't show plus, but I'll just note it's a positive number. Because if I came in and I put red on H, black on A, I would just get minus 24, right? All I've done is reverse the polarity. I didn't do anything wrong. I measured the polarity in the opposite direction. Okay, now, if I put red on B and black on F, what would I get? So I put the red here and the black over here. 12. Yeah, it's just the 12 volts of these two, because it's on this side of this, so it's not going to get this voltage of this battery, and that one's not connected to it. So I get 12 volts. So let's try this real quick. This is one I didn't ask in that, but let's just make sure we see this. If I put red B, black C, what would I get on that? Yeah, this would be 0. The two wires connected together, there's no voltage drop between them. What if I put the red on E and the black on A? Yeah. So I have E's here connected here, so I get all 6 of those volts and all 6 of those volts, and I have it reversed, so I get minus 12. If I move these and I said red on E, black on B, it would be minus 6 volts, because neither one would include those batteries, they're shorted. All right, does that make it clear? Can we? Yeah. Somebody had those and had kind of struggled with it. I want to make sure. I don't know who it was, but if you look at this circuit, it's almost like you drew it like this. What it is here? If you want to draw the schematic. Well, it's actually not even connected. So we'll draw this. I'm going to draw it like a schematic symbol. Like that. So really, F and G are the same connection. D and E are the opposite ends of the battery. Okay, let's do another example here with our Kirchoff's laws. I'm going to erase all this. I'll make them all different, but I don't know, maybe it's not worth it. What order do we put these in? So I've already put one of those handy dandy tables with the battery, R1, R2, R3, R4, R5. And we want to find the voltage across each, current through each. We might even do the power through each. We've done a lot of these type of problems. Yeah, it's worth going through another one, making sure we have them all down. And I'm going to do this a couple different ways. Okay, approach number one. Let's solve it the way you've been solving. If I gave you one of these last week or the week before, how would you do it? Or if I gave it to you today?
Solve the parallel part on the right first.
So if I take a look, these three resistors are actually all in series, aren't they?
Yeah.
So if I want to solve that, so if I want to solve that, go as far from the battery as possible. And note, R3, R4, R5 are in series with each other. The same current will flow through all three of those. So I can replace those, and I want to replace them with the resistor I call R345, which is just the sum of those. And I think, 120 plus 50 plus 30 is going to be 200.
Yeah.
I can write it out. 120 plus 50 plus 30. I didn't actually mean to make it exactly 200, but it works out. It'll make the next step easier. All right, now I'm going to rewrite the circuit and say this is my circuit I have now. I have a 12-volt battery. Or we go with my first step. Second step would be
Make our 2 and our 3, 4, 5 into 1.
Yep.
Right?
those are parallel. So I'm going to go over here, 1 over the total for those. Let's see, we'll make that, I guess it's just going to be 2, 3, 4, 5. You can come up with different labels if you like, but I think those are clear at least. Is 1 over 200 plus 1 over 200. So it does conveniently work out. It ends up being 2 over 200. And then R, 200 over 2 ends up just being 100 ohms. And if you get used to it, I'm okay with you recognizing if I have 2 identical resistors in parallel, you just replace them with 1 at half that value. It's always going to work out that way with parallel. So I come down here then and I say, okay, 12 volts. I'll do one more. Those are all 3 in series. I'm just going to call this RT for total, for everything. And it's going to be 100 plus 100 plus 150 is going to be 350 ohms. So at this point, I have an equivalent circuit to this. We've replaced all 6 resistors by a single resistor. And I'm going to go back and just use Ohm's law now to solve everything. So at this point, I'm not really using my Kirchoff's laws. I'm using my parallel and series resistance and my Ohm's law. So the current through this one will be 12 volts over 350. Is 0.0343 2857. I'll go 29 amps, or 34.3 milliamps. That would be this current. Which this is a series circuit, so that's also this current. So both of these are the 34.3. Now I can use that current to find this voltage. So this voltage right here is going to be 34.3 milliamps times 100 ohms, which is going to be 3.43 volts. You guys comfortable with me doing that calculation without doing the adjustment? Writing it out, okay. This voltage here will also be 3.43 volts, since it's also a 100 ohm resistor with the same current. And down here, this voltage is going to be, let's see, 34.3 milliamps, 0.15 kiloohms, 5.145 volts. Probably round off to 1.5. Okay, got all my voltages. Now, do you want to look and see what we can relate back to the original circuit, or should we just work on up through the next one? Which works better?
Well, can we start filling in that?
Yes, yes, absolutely. I'm going to take this one. Battery, 12 volts. What other things do we have? I know. What other things do we already know? Well, this 100 ohm resistor is R1, so I can put 3.43 volts in for it. This resistor is R6, so I could. Really? You guys let me do that? You didn't point out to me that I screwed up my table?
Didn't notice.
I know, I didn't either. That's why I'm blaming you instead of me. I'm trying not to take responsibility.
I just noticed how your handwriting got progressively worse the lower you got.
Yeah, I know. I'm really sore today, so I don't feel like bending over to write. And they put these, they actually put the boards a little higher than normal anyway, probably because I'm teaching this. All right. So now you're gonna make commentary on my handwriting, huh?
Well, I mean, I don't blame you.
It's okay. I'm not offended. It's true. That's awesome. You notice when I do like those,
R6 isn't that though.
what?
R6 is not 3.43 volts though.
Oh crap, you're right. R6 is 5.15 volts. Thank you for paying attention. All right. And the current that's flowing here through all this resistor just represents these four over here. So it's the same current that flows through R1 and R6 and the battery. So I can actually go put those down. 34.3 milliamps, 34.3 milliamps, 34.3 milliamps. Look at that. I can fill out one more value right now. See where it's at? This voltage is across that resistor, right? When I go up here, if I were to write them down, this voltage and current would be flowing in here and here. So if I were to look right here, I would have 34.3 milliamps flowing through these. So these voltages, if I wrote them down, would all be the same as here. I'm not going to bother because I've already filled the table out and I just clutter it up. But due to the junction law, when I come into here, this 34.3 milliamps will split. Okay. But from the loop and from what we know about parallel, we already know those two resistors are represented by the single one. And those two resistors are in parallel, so they'll have exactly the same voltage, which is the same as here. So I would have 3.43 volts across both of those, right? Because that's what I have across that resistor, which represents them. And this is actually R2. So R2, 3.43 volts. And in fact, if you check, outside of a rounding issue, this plus this plus this equals 12 volts, which it needs to. If I go around this loop, I should sum to 0. Looks like it's going to end up being 12.01.
Yeah, close enough.
Yep. So that loop sums to 0. Over here, this loop ought to sum to 0 when I'm done. I got 3.43 volts across here. Current, what are those currents? Well, current is 3.43 volts over 200 ohms. I'll tell you, since they're identical resistors, I'm just going to split that current in half. It'll be like 17 point something. It's 17.1 milliamps. So both of these are 17.1 milliamps. Okay, so that means through this resistor, there's 17.1 milliamps. Through these three resistors, those three are represented by R23, there's also 17.1 milliamps. Okay, just a note here, these three are all the same, 3, 4, and 5, because they're in series, so they have to have the same current. Everything in series has the same current. They happen to be the same current as R2 only because their combination is the same resistance. In a normal case, this current would be different from this one. It's only going to work out this way because those are 200 ohms, that's 200 ohms. Now I can go back and say, you know, I've got 17.1 milliamps through here. I know what is this, 3.43 volts across that resistor already. I can go calculate these voltages for each one of these. Just take my current, 17.1. I go 2.05 volts, just use an Ohm's law. .855 volts. That's 30 ohms, so 5.1, oh, no, 0.513 volts. So 2.05, 0.855 volts, and 0.513 volts. And if I check my loop here, it'll all sum to 0. If I go this direction, I'll go up 3.43, and then I'll take the steps down and end up back at 0. Loop all applies to that loop. I can go through and do powers now, which I'll do just for completeness. I'm going to do it quickly though. 411.6 milliwatts. I'm just multiplying as I go across the table. 117.6 milliwatts. Oops, put the wrong number in my calculator. That's going to give me the wrong value. If I check, all the powers across the resistor should sum to that power. Over here, note, I can't add up voltages here. I have to add up the correct voltages, right? If I go around this loop, this plus this plus this plus this is 0. In other words, that plus that plus that is the same as 12. If I go around this loop, this plus this plus this plus this is 0. So I think students will get here and get so used to, I can add those voltages up. No, you can't. You only add the stuff, it's only the stuff that it applies to. You have questions on this? It's one more problems like last week. A couple of people had issues on actual work now. Go ahead. How we doing? Let's try the loop. Let's try using, this might still be the easiest way to do this. Last week, didn't we do one that had 2 batteries in it, which is probably even the harder one? I have it out there, it's recorded. I could do this one with a loop, setting up loops and solving it. So let's do that real quick just to show us that it works either way. So let's take this and clean up our picture a bit. We're all done. We should get the same exact answers. Oop. Let's try that. If I were going to set this up, I'm going to use my Kirchoff's laws. If I look here, I have loop 1, So if I work my way around here, I'm going to call this loop 1. I'll work around here, I'll call this loop 2. If I look right up here, I have a junction. I also have a junction down here. Either one will give me the same equation. All right, now I'm going to go in, I'm going to assign current. So I did that. Let's do the other in blue, just kind of keep it. So I got the different color markers. Let's take it back. Well, I think it's a little easier looking up here not to have this blob of black, but to have a little bit of red and blue. So if I go around through here, through R6, through the battery, through here, I'm going to call that I1. I'm going to have I2 go through that resistor in the middle. If I go over here, I'll have the current, and I'll just draw it around here. And yes, I can draw I3 in the direction I want. I can draw I2 in the direction I want. If I guess the wrong direction in the end, I'll get a negative number. Okay, so at my junction, all the current in I1 equals all the current out, I2, I3. It's not too bad, is it? Now let's work our way around loop 1. So loop 1 says if I start, I'm going to start right on the side of my battery and work my way around. Might be easier to start here, so I'm going to go up 12 volts. I gain 12 volts. So I'm going to put a big plus to make sure I'm gaining voltage. Then I'm going to go across this resistor. And when I go across the resistor this direction, I'm going to lose voltage, right? I'm going to assume that's my polarity. So I'm going to just say, well, I'm going to take and subtract 100 ohms times I1. I don't know what the current is, so I got to solve it. Another resistor. And then I'm going to go down here, and I will go from high voltage to low. So I'm going to drop, so I'll have a negative, which is a 200 times I2. And if I go over here, I'll assign a polarity. Same direction, I'm going that. In the direction of current, I'm always going to drop voltage on resistors. So I'm going to, what was it, 150? And that whole thing sums to 0. Now I'm going to take this, oh, that's not I3. I did that wrong, right? That's I1. There's no I3 in that loop.
You were in I1 twice.
Yeah, I go through I1 twice, because this has I1, this has I1. And I have I2. I3 is not inside this loop.
What about R6 down there?
R6, the current that flows through R6 will flow up through the battery and through R1. It's all going to be I1. I3 is only going to be the current through those 3.
Oh, I was reading that wrong.
So, and that's, I wrote it that way to start with. Now, what I'm going to do up here real quick before I go on, I'm going to simplify this equation as best I can. First of all, I'm going to say, okay, I'm going to get rid of units here. All my volts, I'll have things in volts, I'll have current and whatever they end up being, and I have ohms. So to make my life easier, I have 100 ohms and 150. So put them together, I get 250. I'm going to drop the ohm symbol and just write I1. I'm going to drop the ohm symbol and just write I2. There I have an equation for loop 1. So just an algebra equation. I could replace I1 and I2 with X and Y if you want. I can't solve it, right? I've got one equation and I have 2 variables. One equation, 2 unknowns. Actually, no, I got 2 equations, but I got 3 unknowns. All right, loop 2. Where do you want to start on this one? Down here and work around maybe?
Sure.
I'll get the same equation wherever I go. So now be careful. If I go this direction against current, I'm increasing voltage. So I actually get plus whatever R2 is, 200 ohms times I2, because I'm going in the direction. So this is all about polarity. If I go across here in the direction of current, I'm going to go down 120 ohms times I3. I'm going to go down 50 ohms times I3. I'm going to go down 30 ohms times I3. So if I'm going from plus to minus, I'm dropping, so I'm making a negative. If I'm going from negative to positive, I'm increasing. Even though this is really being created by current flowing, it's by polarity. All right, now simplify it. If I go around here, I could take this and write this just 200 I2, 120, 170, 200. Three equations, three unknowns. But I think the bottom equation I can solve pretty easily. I mean, I can't solve for a number, but I can simplify it, right? I can look at this and go, hey, this is 200 I2 equals 200 I3. Divide both sides by 200, therefore I2 is exactly equal to I3. That's what we found on the other one. Since this is 200 ohms, also ended up being 200 ohms, so that big identical currents. So now that I've done that, I'm just going to draw a little break here, right? And in fact, I'll put it in these just to make sure we keep it clear. All right, so I have three equations going on. So I'm going to take this one, but I know that I3 equals I2, so I can plug that in. I'll put in like little parentheses there just to know. I just, substituted I3 is equal to I2, so I2 plus I2. Okay, so I got that. Now I'm going to take this equation, solve it down here, and see if I can keep it neat for you. So I'm going to take 12 minus 250 I1 minus 200 I2 equals 0. But I know I1 is 2 times I2. I can substitute either way, but maybe I'll just put that in. So 12 minus 250, I1 is 2 times I2. Now I can go and let's see, this is 500. Add those together, I'm going to get 700 I2. That one's pretty, I'll just move it right over here. So I can move it to the other side and rewrite. So I have 700 I2 equals 12. So I2 equals 12 over 700. If I go back, this was volts, this was ohms, so I'm going to get amps out. Calculator's in my pocket. 12 over 700 is not a number I can do in my head, so get my calculator. Lo and behold, this is 17.1 milliamps, right? 0.017 amps. Does that sound familiar? Same one we got the last time, didn't say other. So that's what I2 is. I know that I3 is equal to I2. So that's also 17.1 milliamps. I know that I1 equals I2 plus I3. So that's going to be what? 34.2 milliamps. So now I have all my currents. So I can go back here now and say, okay, I1 is what I had through R1, R6, and this, so that's 30, okay, that's 20 volts. No, 17.1. Sorry. 4.2 milliamps goes through R1, 34.2 milliamps, goes through R6, 34.2 milliamps. Okay, I2, which goes through R2, is 17.1. I3, which goes through these three resistors, is also 17.1. So it'll look like what we got to do it the other way. So both of these work just fine. Either approach. This might even be a little easier now. It's a little more messy when you don't have this and those line up so nicely. But, so Kirchoff's laws give us this way to solve this. And again, like last week, if I got rid of R4 and put a battery over there, and you have to do one of those in lab this week. So 2 sources. You got to solve everything. The only way to do it is to set up these kind of equations and do some very tedious algebra with 3 equations and 3 unknowns and work through. I'll give you, do you need me to go do all the voltages and powers? They're going to be the same as the last one.
Oh, good.
That good?
This way seems way harder.
Does
The
it?
other way, yes.
Well, there's a reason we teach it later.
Yeah.
Here's the thing, as long as you have a circuit that's strictly resistors with one source, you can do it the way we've done it in the past. You can simplify the circuit down. That's why we do those. And that's why we do those first. But as soon as I have a problem, like I said, like last week, you're gonna build one this week in lab, where you're gonna use 2 independent power supplies. You can use the 2 independent power supplies in the GWN stack supply over there. But you gotta solve them. If you have this supply, a resistor, a resistor, a resistor, and this supply, there's no way to solve this one outside of using these types of equations. And the thing is, I will not in here make you solve more than 3 equations and 3 unknowns. Okay, I'm gonna be nice enough, I'm not gonna do more algebra than that. But you can expand these as far as you want. You know, if you went and set an electrical engineering circuits course, you might end up with 11 equations and 11 unknowns.
And is there to use a part of both sides?
And you can solve those, like I said. And you can solve them just fine, but you know, it just ends up being a ton of algebra, or you learn some matrix stuff. You maybe did at the very end of algebra when you did it, that can solve those. Not terribly difficult, just tedious is all it does.
Yeah.
So, the other thing we can do is you can go into an equation, you can go to an emulator, multi-sim. You can sign up in multi-sim and try this. They updated stuff in the fall, and I don't know if you can. You used to be able to do those in the free version just fine. You can sign in, create yourself a little account, go try them. I'm not sure if it will let you do those anymore. I think it only lets you have up to 4 circuits, so you can have one, just keep replacing them. But you can go to multi-sim, which you look for online. So they're trying to, they have this nice, it's an incredibly good simulator and very easy to use. And for years we used it in the free version and it did everything we needed in classes. And then just last fall I noticed that gatekeeped it, so
Is that like
you gotta pay like some bucks a month for it.
Is that the same as that? What's the one you showed me? Like Fallstad?
No,
Is that the same thing?
no. Fallstad does just strictly, I'll write that down for you guys want to look at that. But you know, Fallstad would probably do this.
I've used Fallstad a couple times.
And Fallstad's all free. I like it. I think it's hosted by a school or something, so it's designed for students to play around with. It would actually do that just fine. I didn't think about that. Multisim is one that there's an old software program that's been around forever since the 70s for solving circuits where it used to just be all text you type in. And Multisim is built on top of it. I just lost the name of it. But anyhow, it's a nice one. You can design your circuits on there and you can hit simulate, simulate it. And other places you put little probes and meters, they'll give you voltages and currents through it. It's a really good way to do once I start to get more involved. And like I said, up until like the middle of fall somewhere, it was the free version would do everything I needed to do to check even more advanced circuits in here. And then they put cut off and made the free version pretty, like, you can have up to 4 circuits total, and you can have up to like 6 circuit elements in it or something. Which I guess that's 1, 2, 3, 4, 5 circuit elements, so I think it would probably work. Multi-sim will do just things like put in full transistor amplifiers and emulate the whole thing. Sorry, Dan, you were asking me on R2 earlier, or R1 or R6 or something like that.
I don't remember.
I'm sorry. I was trying to get the two things going. Now, we did do this whole circuit before you got here that I have recorded, the way we've done it before. So I'm just, this week, we're focusing on Kirchoff's laws. Last week, we talked about them, but we're really focusing on series and parallel. I'm going to encourage you this week, work on thinking of these Kirchoff's laws as you do the assignments. So we'll be ready to move forward from it. You just, and I understand they're tedious to work with, and one of the things that happens is once you can work this circuit with the Kirchoff's laws like I did, even though it's tedious and it's a lot of algebra, you gotta do a lot of substitution. Once you can do that, what we'll do next is we'll say, we do know that's tedious, so we're gonna simplify it. That's what the core of this course is. It's different ways I can solve that circuit and even bigger, more complex ones. Set them up mathematically so I can solve them a little easier and know what's going on in them. And then in here, of course, we'll always build them. Yeah. And this week, you're going to build labs. Hold the video.